Thank you. Okay, let's start. Today we're going to discuss uh, the moment of a force, first in 2 dimension, and then we have a problem in 3 dimension. So let's start with an overview of what you've learned in the lecture. Well, now you know that we know that the cross product of two vectors is represented by this V equal to P cross Q. And actually, if you have P and Q in a plane, then the cross product of P and Q would be a vector normal to that plane. So how we're going to calculate this cross product? Well, it is kind of like a determinant of a matrix, very similar, but the procedure is like this. If you want to calculate P cross Q, and pay attention that it is important how you put this here, P first and Q is the second vector. So you will draw something like this. You put ijk on top, and px, py, pz, which is the first vector, on the second row, and qx, qy, qz on the third row. And when you want to calculate each of the component, well, the cross product is a vector, so it should have three components in three-dimensional space. So when you want to calculate each component, you have to, the best way is to actually do something like this. You can let me. Okay, let me see if I can work with this pen. All right. So, well, imagine you want to calculate the x component of the v vector, which is the cross product of p and q. Then you cross ijk, which is the first row, and also the first column. I'm doing this for v of x. So you cross ijk and cross first column, and then multiply py by qz, which are the diagonal elements of the remaining matrix, which is now this one, py qz, and and minus pz qy. This is how you calculate v of x, py qz minus pz qy. And then you can do the same for Vy. You cross ijk and cross the second column, and then you're going to have a 2 by 2 matrix, which is Px, Pz, and Qx, Qz. This is for Vy, and then multiply Px by Qz and subtract Pz Qx, and this is Vy, and you do the same for Vz. You cross the third column, and then you would have Px, Py, Qx, Qy, and multiply the diagonal elements, Px, Qy minus Py, Qx. And this is how you calculate the components of the V vector. And the magnitude of this vector can be calculated by this equation. P is the magnitude of the vector P, Q is the magnitude of vector Q, and multiply it by sine of theta, which is the angle between P and Q. All right. Is that clear? Any questions? Okay, let's move on. Then, all right, if you want to, actually the moment of a force is defined by the cross product of the displaced. Let's see. Well, if theta is the angle between P and Q, it will always be sine of theta. But as you know, sine of theta is equal to cosine of theta plus pi over 2. So you can actually do this. So you can substitute sine of theta with cosine, but there's no need to do this. When you have theta, then you simply calculate its sine. And yes, the magnitude of V is square root of Vx squared plus Vy squared plus Vz squared, which is the definition of the magnitude of a vector. But when you have the magnitude P and Q, then you don't need to calculate V based on the procedure I described. You can simply take the magnitude of these two vectors and take the angle between them and calculate the magnitude of the cross product. So if you don't have P and Q, then you need to calculate the vector V and then calculate the magnitude of V by the Pythagorean theorem. So Pythagorean equation. So this is actually equivalent to Vx squared plus Vy squared plus Vz squared. Yes, I think so. All right. I was answering Julian's question. Actually, I'm not sure if this discussion is going to cover, but you can refer to the syllabus you have and check check that. We are going to solve problem 320, I think. So you can check in the syllabus of your midterm exam whether our discussion covers everything up to that point or not. Okay, we define the moment of a force about a point by a cross product. R is the actually the position vector of your force. It is actually the place that your force is placed. So in this figure, you can see that force is placed in point A. So the position vector would be R, which is from origin to point A, and you cross product R by F to calculate the moment of this force. So based on what we discussed about the cross product, you have moment defined by this, and you are going to have mx yfz minus z fy, and my z fx minus x fz, and mz is equal to x fy minus y fx. And moment is a vector, so you're going to have three components, and you call component in x direction mx, and you have my and mz for the y direction and the z direction. And the magnitude is also the magnitude of the position vector, and the magnitude of multiplying by the magnitude of the force and multiplying it by sine of theta, which is the angle between the position vector and the force vector. And this is going to be, if you see this figure, we have angle theta between position vector r and f. So you're going to have an equivalent theta here. And if you multiply the length of position vector by sine of theta, then you will get d, which is the opposite length. And so you have here r sine of theta would equal to d, and you will have fd for the magnitude of the moment of this force. And if you have multiple forces, then you're going to you have to sum them up to get the total moment. Actually, you can calculate each force's moment and then sum them up to calculate the moment of the total moment. Okay. Is there any question? Well, imagine you have a force in 3 dimensions, then you can decompose that force into 3 vectors, which are along each of the axes x, y, and z. You can calculate the moments. For example, you can have m naught of x equal to r cross fx and we can have m naught y equal to r fy m naught z fz. And if you sum these up, you're going to get the total moments. So this is equivalent to get to cross product R by vector F. Okay. Is there any question about this? All right, let's solve a problem here. We have a rod. This is a two-dimension, which is in a plane. So this is a two-dimension because both the rod and the force are lie in a plane. So we have a support in point B, and you're exerting a force by the amount 20 pounds on point A, which has an angle alpha with the horizon, and we also have the angle of this rod with respect to the horizon. So here we want to calculate the moment of this force about point B. So we have to first figure out what the position vector is. So this is going to be R, and this is also force vector. So M is equal to R cross F based on the definition. But this is a two-dimensional case, so we're not going to bother ourselves with the components, and we'd rather write this M in a scalar, actually. So in the problem, it is proposed that we can actually decompose the force into components along AB and the perpendicular axis to the AB, and then calculate the moment. So what we're going to do here, this is the free body diagram. You have the force, and first you have to make your coordinate system. Imagine, for example, this is the x direction along line AB, and Q on perpendicular to the AB. So you have two coordinates, P and Q. So you can decompose this force to P and Q, and then you can say that P would not exert any moment around point B. And physically, it makes sense because it is along this direction, so it is going to just compress the rod. And it is not going to rotate the rod. The only force that tends to rotate the rod is the component in the Q direction. So we can neglect the P force, and well, from definition, you have RF. So if you say, for example, imagine P is the position vector along P direction, and let's let's say RP, and P is the force along the P direction. So actually F is equal to P plus Q. So here you have R of P along line AB and also force P along line AB. And so the theta would be 0 between these two angles, and therefore M, which is equal to RP P sine of theta, would equal to 0. So mathematically, we can also prove that this force does not exert any moment. Then you would only have Q here that contribute to the moment around point B. So let's first calculate the magnitude of force Q and P. You have 65 degree here. Then this angle is going to be 65, and so this angle is 90 minus 65, and so let's call it alpha. So theta would be 90 minus alpha in this figure. So you would have 90 minus I'm sorry, alpha, I should correct alpha. Alpha is 65 minus 25. Alpha 65 minus 25. And then you would have 90 minus 65 minus 25, which is equal to 50. So you have the angle, and you can take the component as Q, the magnitude of the force, times cosine of theta. And it would be 12.85 pounds. And the same manner, you can calculate the magnitude P, which is 20 sine of 50. So you're going to have M of B, Q RAB sine of 90, which is the angle between Q and R of P, as I didn't note it here. And it would, well, this is actually the total of two moments. So this is, you can call it MQ, and you can call this MP. So this component, as we discussed, is equal to 0, and you would only have moment from component Q. So MB would be equal to 115 pound-inch. So you should be careful also about the units. The moment has unit of force times displacement, because it is the cross product of the position vector and the force vector. So you have to be careful about the unit. All right. And well, you can also calculate if you have the magnitude of the position vector r and the force, and also the angle between them, then you can calculate the magnitude of the moment by this formula, and you can draw the force and the position like this, and then you would have an angle alpha here, which, if you want to be exact, then you have to displace the vectors. Actually, you have to put the initial points of two vectors at the same point, and take that alpha as actually let's call this alpha star. Then alpha is going to 180 minus alpha star, but it doesn't really matter because sine of alpha is equal to sine of minus alpha. So if you take this angle or this angle, it doesn't really matter, because I'm sorry, it is going to be there's going to be a minus here. So well, this is the magnitude of a vector. You're not telling about the direction of this vector when you're talking about the magnitude. So it should always be positive. If it is the magnitude of m, then it is always should be greater than 0. So if you take alpha star here, then you're going to have m a negative number for m. But if you get alpha, you're going to get positive. But the magnitude is the same. It's just the sign that differs. So you're going always you have to always get a positive amount for m. So if you're multiplying fr by sine of alpha star, then you have to drop the sign. So it is basically, by definition, this alpha is the angle between r and f. So this is the right angle from geometrical point of view, but doesn't make any difference about the magnitude. Yes. Well, you can tell from the figure how is the moment oriented in this space. This is a two-dimensional case. So this force is going to rotate this rod clockwise, right? So you actually you can have the the direction that this moment is imposing. So when it is, well, imagine this is a 3D problem. So you're going to have x, y, and if you use the right-hand rule, then you're going to have z direction pointing out of the plane. So this, when it is out of the plane, it means it is clockwise. But in two-dimensional cases, you don't have to worry about the right-hand rule, because by just seeing the force, watching the force, you can tell how it is going to rotate the object it is exerting on. So this is in this direction, so it is going to be clockwise. And also positive, because it is going to be along the z direction that is coming out of the plane. From method one, where is force Q coming from? Well, it is the component of the force in the Q direction, and you can multiply the length of force vector by cosine of theta, right? So here actually you have two components, so this is going to be F cosine of theta. All right. Okay. Is there any question about this problem? So we discussed two methods. In the first method, you decompose the vector into two components. It would be better if you choose the components in the along the rod, because then this force would exert no moment on the object, because there's no angle, that the angle between them is zero, and you would only have to calculate the moment that is exerted by force perpendicular to the rod. And in the second solution here, because you have the magnitude of F and R, and you have the angle between them, then you can easily use this formula, FR sine of alpha, to calculate the moment. So whatever method you use, you get the same answer. All right, let's because well, based on definition, when you have mfr sine of alpha, when you want to use this formula, then this alpha is defined by the angle between two vectors. So the position vector actually is defined by the initial point, which is the origin. Here is B. Well, you want to calculate the moment around B, so B is the origin of this position vector, and ends at A. So you have the vector in this direction, and you have F, which is given in the example in this problem. So if you want to calculate alpha based on definition, this is the angle between these two vectors. So alpha star here is not the angle. Actually, it is alpha, but you're going to get same magnitude if you multiply it by sine of alpha, but with a minus sign. So the magnitude would be correct. That is what you're concerned about. You want to get the magnitude of this vector. So it doesn't really matter if you use alpha star or alpha. This is problem 3.2 from your textbook, I think. All right. Okay, let's go and review the definitions in three dimensions. We had from before that a vector in space is defined by is magnitude times the unit vector, which is along the direction of f. Yes, exactly, Julian. Is there any other question about the last problem? Uh, well, you can use both methods whenever you want. Mm, in this problem, it doesn't really matter whether you use method one or method two. But let me think if there's any case that you can't use method one. Um, well, mm, maybe it is best not to use method one uh, when you can't decompose a vector to components that one of the components or is not exerting any moment. So then it is best not to use this method. Exactly. FD is equal to FR sine of alpha. So you can use that. Actually, D here would be this is D. This is that was an equivalent form for this F. Yes, the shortest distance is the distance along the perpendicular direction to the force. Yes. Is everything clear? All right. Shall we move forward? All right. So you have this definition, which is magnitude of force times the unit vector along that force, and the unit vector is actually uh, the vector uh, divided by its magnitude. So then it becomes normal, and we call it a unit vector. And so when you first, if when you want to find the moments in 3D, you first decompose. Now, actually, first you write each vector based on this equation, and then sum all the vectors up to get the total force, and then you calculate the distance vector or the position vector, and then calculate the moment. We have a problem here that we're going to use this method. But we have a small boat, and we have two pulleys. Actually, um, we have a rope that is connected to point D and then comes to this pulley, and then comes down to pulley A, and then comes down to pulley B, and then goes up to a fixed point A. So, well, think about how you're going to draw the free body diagram for this. Actually, this is a single rope, continuous rope. So the force along this rope is equal. It doesn't matter where you cut the rope to get the force. Yeah. And we are asked to calculate the moment about point C. So actually you have to sum all the forces at point A to get the resultant force, and when you get the resultant force, you calculate the distance vector and then cross product that force by distance vector to get the moment. Let's see how it goes. So in a free body diagram, at point A, you're having a force that is downward, which is the force from the rope, and you have another force still downward, which is exerted from the pulley to point A, and another force which is along which is along AD. So you actually have three forces exerting on point A. Is there any question about this? No questions? Is the free body diagram clear? Because I know this pulley thing is a bit complicated. Oh, we have three forces. Let's say we have a support at A, and well, you have a pulley here. So to this point A, you have a force from the rope AB, right? It is clear. There's a support at point A that the rope is connected to it at point A, and at the same point, well, if you're skeptical about whether this is the same point or not, it is actually, if you want to be very precise, it is something like this. We have a pulley here, and then small distance from it, you have point, let's say A, you have a rope here, you have two ropes here, and then you're going to have a force. Let me draw it again. So you have a force FAB. You have another one, let's call it F prime, and F double prime. So when you want to draw the free body diagram, you should always be careful that to draw all the forces that are exerting on the same object. So here we have these 2 points at the same place, so we can safely that they're at the same point. All right, thank you, Carolina. Is that clear? Well, imagine that the object that we are considering the force acting on it is something like this. So uh, actually you have a point that is connected to the pulley, and you have another point that is actually the fixed support that supports the rope AB. Then if you consider this one as an object, then you're going to have these 3 forces, but this distance is very short that you can actually impose all the 3 forces at the same point. So we're not going to consider this distance. This is our object, and we have 3 forces on it exactly exerting at the same point. Yes, because you have 2 forces. Yes, exactly. They are the same. As it was given in the example, all these 3 forces are actually the same. The magnitude is the same, but the force vector is different because uh, we have a different direction for force AD. So the magnitude of these forces are exactly equal because they are exerting. They actually they are in the same rope, so they should all be equal. Is that clear? Okay, we don't have time. All right, in the first step, you should you should get the magnitude of each force and multiply it by the unit vector. So, for example, for AB, we know that it is along the y direction, so it only has y component, and it is in the negative direction. For force AD, you have to calculate the direction because it is not obvious. So you have the magnitude of this force times vector AD over the magnitude of the vector AD. So this is the unit vector. Then for AD, then you can easily calculate that the displacement or the vector AD by subtracting the coordinate at A with D. So you're going to have 6 for the X direction, 7.75 in the Y direction, and 3 foot for the Z direction. And then multiplied by the magnitude of the vector, and then you will get force AD, F of AD. And then you have to calculate the resultant of these 2 forces, these 3 forces. You have 2 F of AB because these 2 are exactly in the same direction and they have the same magnitude, and added added by FAD, so you get the resultant of these force. Then uh, you need to calculate the displacement vector, which is along line CA. This is the origin at point C, so the vector is from C to A. So you have the dimensions, and you can get R from C to A, and then you can calculate the moment by the cross product definition. Use cross product definition for 3D case because it is hard to calculate the angles. So the only way you can calculate the moment is to use this equation, and you will get the moment around point C. So if you have any questions about how we derive this moment at the end, then let me know. I'm posting the videos, but I will post the 3 last discussion slides as well. Sure, I forgot to do that for the last 2 ones. What do you mean by prompt? Uh-huh. Okay. Uh, Actually, I don't know. You can get back to your syllabus. All right. We're going to have office hours from 2 to 4 today because tomorrow is holiday. All right. Is there any question? Yes, he's going to be there from 3. You're welcome. Uh, have a great time studying for your midterm exam. And I think I will see most of you on Wednesday. Have a great one. Thank you.